Hey, it's day 2, unit 15. We're talking about probability and percentiles using a normal curve. So in yesterday's notes, you should have talked about, or you should have looked at the notes, I hope, that talked about what a normal curve looks like. So it can be called a bell curve. It's when you see this type of thing, where everything kind of clumps around the center. Some are above, some are below, but the majority is right here in the middle. That's essentially what a normal curve is. So this first part here is saying Kevin's math grades are steadily improving. His test average is now an 88. Yay, Kevin. The mean of all students' test scores in the class is 91, standard deviation of 3. It says assume test scores in the class follow a normal distribution. That's actually something that's pretty important. You can't assume something's normally distributed, so any question with it should always say it follows a normal distribution, all right? Or maybe it's going to ask you about it, but otherwise it should tell you, all right? So when it says calculate Kevin's z-score, right? A little review. Z-score is his actual score, 88, minus the mean. So the mean was the 91, and then here was his 88, divided by the standard deviation. Right, so you get -3 over 3. We get a z-score of -1. So that's a nice, pretty z-score. So it says, does the z-score suggest that Kevin did better or worse than the average math student? Well, worse, because if it's negative isn't always bad, but what negative does mean is it means you're below the mean. So in terms of grades, yeah, below the mean's not good. If it was like blood pressure, yeah, it's great to be below the mean. Low blood pressure is good, or golf score, lower is better. But so it just depends contextually. In this case, it means he did worse than everybody. All right, on the curve, it says label the mean and the standard deviation of the class scores and put a star on Kevin's scores. All right, so the mean is always represented by the 0. So it's dead center here. So that is the 91. Right, Kevin is 1 standard deviation below the mean, which makes sense because if you go 3 points below, there's 88. So we can put a little star right there. There's Kevin. All right. And then if you want, you could go 3 above and say there's 94 and 3 above that. So if you're 1 standard deviation above, you'd be 3 points. 2 standard deviations above, it'd be 97 and so on. All right, which kind of makes sense because 3 standard deviations above, that would be about 100, which should, it says technically there's 0.1 above here, but this is approximate. So when it says what % of students are doing better than Kevin, all right, you can add up everybody above this, right? So you can add all percentages above Kevin's, score, or, right, we can approach it a little bit differently. So let's take this approach. If we add everybody up, so we're going to add everybody from here over. So all of this, okay, that means we would be adding the 15% plus 19.1, and then keep going, another 19.1, and so on. All right, now something you might realize, dead center to the right is 50%, to the left is 50%. So you could even say, all right, let's forget that, do 15 plus 19.1 plus 50%, and that would cover it right there. Right? So if we grab our calculator, if we do 15 plus 19.1 plus the 50, 84.1. So that's the percentage of students that did better than he did, all right? That's a lot of students right there. When it says Kevin is doing better than what percentage of the students, well, in that case, you could add up everybody to the left. So you could add all the percents below Kevin's score, which means to the left, whereas up here it was to the right, right? Or you could do 100 minus the values above. So there's a lot of ways to do this. Otherwise, you can add up the 0.1, 0.5, 1.7, and so on. I'm going to go the faster route and go 100 minus 84.1. If we do 100 minus 84.1, that'll leave us with 15.9. And we could have taken that approach up here. We could have said, hey, we've got the full 100% here, except for this part. And we could have taken the approach back with that. So keep in mind, lots of ways to get to that answer. All right, last part. It says shade the percentile Or the area to the left of Kevin's grade. That area is the percentile. All right, well, I kind of used my yellow, so I'll use my blue for this. So this, everything below Kevin's score, that's the percentile, right? So when you guys have taken like SATs or PSATs and it tells you what percentile you're in, this means I'll round it and say he's in about the 16th percentile. That literally means, all right, you did better than about 16%, and 84% did better than you did. Right? So percentile, it doesn't mean that you got a 16% on the test. It's a comparison to, your peers. So if you're at the 50th percentile, that's actually not bad. That means just you're kind of average. You did better than 50%, 50% did better than you. 16% tile is not great, but this is obviously a really smart class if the average is a 91. So he's still doing great. All right, let's move on. So percentile, let's get that written down here. Okay. So when it says the definition, let me slide so you can see me. The definition of percentile, right, is the percent of people that lie to the left or below. So I'm going to kind of say it both ways. Left or below, right, of that value. So something to keep in mind. If you're all the way to the left, you would literally be at the 0% or 0 percentile, right? If you're all the way to the right, that would be 100%. Right? So you literally read the graph from left to right. And sometimes that gets a little confusing to people. So all the way over to the left side, over here, you'd be at the 0 percentile, 50th percent, all the way up to the 100th percentile. So if you're at the 100th percentile, think about what that means. You did better than everybody. That'd be pretty awesome. All right. When it says here, you took the SATs, you did not receive your numeric score. Whoops, sorry, off the screen there. For the math portion, testing service only stated that you scored in the 97.7 percentile. See right there, I'd be like, done. Thank you. I'm awesome. The mean score is 525, standard deviation of 100. So what score did you get? Okay, so they're basically asking you to figure out where in this chart is the 97.7th percentile. Couple ways that you could do that. I could start at the left and I could count all the way up until I hit 97.7, or I can start at the right and work my way down. So we said all the way to the right is 100%. So what I mean by work your way down, let's take 100% and let's subtract the 0.1. Oops, except for I added 100% minus 0.1. Woohoo, there we go. All right, so right here, if you're on the 3, you'd be at the 99.9th percentile. Let's subtract another 0.5. Right here at the 2.5, you'd be at the 99.4, and I can keep playing this game. Let's subtract 1.7. So right here, if I was at the 2, I would be at the 97.7th percentile. That's what I care about. So at this point right here, that's the 97.7th percentile, which sometimes I do cheat and write the percent sign and then aisle next to it. So just so I don't confuse you. All right. That means if you're here, if you're 2 standard deviations above the mean, because that's what this 2 represents. This is 2 standard deviations above the mean. That means that when the data is normally distributed, like it is for an SAT, that you would have done better than almost 98% of the kids that took it. All right. If we lay out the scores, let's take a look at like what they gave us. They said 525 is the mean, so that goes dead center. So 525 is right here. Each standard deviation is 100. So if I go 1 standard deviation above, that's a score of 625. If you go 2 standard deviations above, that would be like getting a score of 725. So when it says, what score did you get? Well, there you go. All right. You would have to take the mean. Oops, let me slide down here a little bit. You'd take the mean, and we're adding 2 standard deviations to it. Or if I use my symbols, you'd take X bar and add on 2 of those sigmas. Right? So 525 plus 2 of those standard deviations gives you a score of 725. Ta-da! Hi, Gracie girl. No, not yet. Give me a little time. All right. It says your friend is really bad at math. Oh, that's unfortunate. She was in the 6.7th percentile. What score did she get? Okay, 6.7 percentile. Start on the left side and keep adding up until you hit 6.7. So if we do 0.1 plus 0.5, you know that's not enough. Plus 1.7, still not enough. Oops, I'm so sorry. I'm adding and I'm off the screen there. Plus 4.4. There we go. That's it. So I want to include this chunk, and the 4.7. So I'm right here, which means to be at the 6.7 percentile, you have to be 1.5 standard deviations below the mean. All right. There's the 6.7th, and I'll use my abbreviation there, percentile. There we go. Okay. So when it says, what score did she get? Well, you have to take the mean and then subtract 1.5 standard deviations from it. So that's how you use those z-scores. That's what they stand for. So let me slide this up just a little. So that means we're going to take the mean and subtract 1.5 standard deviations. Or I'm going to take x bar and subtract 1.5 sigmas, like that. All right, let's plug in the numbers. 525 is the mean. Subtract 1.5 standard deviations at 100 each. Well, that's fairly simple math. That would just be minus 150. And when you subtract 150, that means she got a 375 on the math portion. All right, not the end of the world. So something to keep in mind, being away from the mean isn't necessarily awful. I mean, I'm not going to fib, that's not great, but it just depends how spread out the data is, how big the standard deviation is. We're going to skip number 3. Let's go right on to example number 4. So on number 4, it says, what if your score doesn't fall on a whole or a half standard deviation? Because the ones that we just did were 2 above, 1.5 below. Those are nice and pretty, right? In that case, your z-scores, we can use the calculator. So the calculator will do it nicely for us, right? So let's do it with this particular example. It says the top swimmer at FHS swims the 50-meter backstroke on average in 39.7 seconds with a standard deviation of 2.3 seconds. Now, how would they know this? They would have had to put like all their times in and do like one variable stats, and they'd get that stuff. So you can actually calculate these things. It says, assuming the situation follows a normal distribution. So there it is. They're telling you that that's happening. Find the probability to the nearest thousandth that she swims her next race between 37 seconds and 44 seconds. So it says, sketch your normal curve with the mean at the center, put the 37 and the 44 on the graph, and shade the area you're trying to find. All right. If we draw our normal curve, do your best. Sometimes they come out a little lumpy. It's okay. We won't judge. All right. So on average, 39.7 seconds. So dead center is the 39.7, right? And then it's saying, what's the chance that she swims between 37 seconds and 44? So 37 would be below it. 44 would be somewhere above it. It doesn't have to be drawn perfectly to scale, but I want you to draw vertical lines, and we're going to shade off that area in between here. Because when we ask what's the probability, all of this together we know adds up to 100%, or you can think about it in probability, it would add to 1. So we want to figure out what's the percentage, right, that lies between those two times.
Mama, can we go on the grass?
Yeah. That is what you're essentially looking for. That's going to give us the probability here. All right, because we know probabilities fall between 0 and 1. We'll just take that percentage and kind of work with it. Okay, so when it says calculate the z-score for each, well, that's from yesterday. So z-score, as a quick reminder, you take the actual score. So I'm going to start with the 37, subtract the mean, divide by the standard deviation, which they told us was 2.3 back up here. All right, and then we'll do the same thing for the second one. You'll do 44 minus the mean of 39.7 divided by the standard deviation. So it's just going to tell us how far above and below those values are from the mean. So if we do 37 minus 39.7, divide by 2.3, the first one comes out to be negative 1.174 if we round to the nearest thousandth. And then the second one, if you calculate it, comes out to be 1.870. So what that actually means is that that lower swim time is just over 1 standard deviation below the mean. The upper one is like 1.8, 1.9 standard deviations above the mean. And now because they're talking about times, the low one is actually the better one. So it's like the golf score, the blood pressure. You want to be faster, I would imagine, right? So what we're going to do is we're going to use these values since they don't fall pretty on the chart. We could estimate, but we really wouldn't get an accurate answer using like the normal curve, going back to this guy. So the calculator will do it for us. This one is going to be the lower value that we need. This one is going to be the upper value. All right. So on your graphing calculator, I'm going to slide this up and I'll show you as I go. It says determine the values that fall in between them. And so what we're going to do is we're going to go to second, VARS, and then normal CDF, because that's what this is. It's a normal curve. The CDF stands for cumulative density function. Don't worry too much about that, but go to second, and then VARS is right. I don't think you can see my finger there. VARS right there. So second, VARS. And then it's not the first one. The first one's PDF. We want CDF. All right. So it's the second one there. Right. And now there might be numbers in there from before. There might not. That's okay. You're either going to clear them out or I would just type directly over them. The lower and the upper are the lower and upper bounds of our little curve here. So the lower in this case is going to be the negative 1.174. So type that in here. The upper was the 1.870 because obviously it needs to go low to high or this isn't going to make sense. And now for this part, that little, it looks like a U, but it's a mu, right? That is going to be the mean, which the mean is 0. The standard deviation is 1. Right? So we're going to type that in as 0 and 1, which they might have been defaulted to 0 and 1 on your calculator anyways, which is fine. Right. Go ahead, just hit paste, which for mine takes me back to the home screen, and then hit enter one more time. Now, for any of you, if you have an older calculator, you have to put them in a particular order. You got to do lower, then upper, mean, sigma, and you have to put commas in between. Yes, there is a comma button on your calculator. It is right there above the 7. So if you have one of like the chunkier old calculators, you're just going to do it in that order. So practice it. Make sure you know how to do this, right? And then what it comes out as is 0.849. And so what that means, that is the probability that she swims in between those two times, right? Oops, it wasn't 0.74. What were those two times? 37, that's what it was. 37 seconds and 44 seconds. So it's the likelihood that like the next race she swims, that her time will be somewhere in between there, right? That's a pretty high probability. So like if you were betting, I'm not a bettor. I can't, it makes me nervous. But if you were a betting person, that's the probability that she would swim between those two times, right? So as a little reminder, the mu, that's the mean. The sigma, that's your standard deviation. So when you bring it back to that normal curve, the mean is always the 0. The standard deviation is always the 1. So that's where it's coming from. All right. So you're going to keep that 0 and keep that 1. All right. I think we have one last page. And we do. And it's still, I think, sticking with that same question. So when it says use the same mean and standard deviation from the previous example, all right, so the mean was the 39.7, standard deviation was the 2.3. I'll just put those on there to remind you. It's saying that, oh, duh, it says it right there. You'd think it was Monday morning. It's not. Find the probability to the nearest thousandth that the swimmer's time is more than 45 seconds. So like she gets a cramp and like swims a really stinky time or something. So draw your chart first. All right. Dead center, that's the 39.7. And it's saying more than 45 seconds. 45 seconds would be way up here. If we're talking about more than that time, that means it would be higher than that or above it. So we're talking about this part right here, all right? In a case like this, you still want to find the z-score. So we just need the z-score for the 45. So we do 45 minus the mean of 39.7 divided by 2.3. Hold on one second. Teddy, hey, no chewing. Here, buddy. Here you go. Here you go. The puppy has taken to chewing the molding. He's a big fan. Not a big fan, though. All right. That comes out to be 2.304-ish, right? What that is, when you look at this area, this is the lower. Up here would be the upper when you're reading it from left to right. So, well, what the heck is the upper? Well, yeah, I know that the normal curve really goes from like -3 to +3, but we kind of treat it like it's infinity. So when we go to type this in, we are going to treat infinity as a really, really big number. Well, not that we treat it like a big number. It is a big number. We're going to type it in that way. So for the upper value, to kind of let it approximate infinity, we're going to type it in as 1 times 10 to the 99th power. And we get to use that little caret key to do it. So on your calculator, here's how we're going to do this again. We're going to go to second, vars, and we're going to do a normal CDF. And I'll run you through that one more time. You're going to give it the lower bound, the upper bound, the mean, and the standard deviation. Now, the cool thing is mean and standard deviation, when I use z-scores, are always going to be 0 and 1. Now we're going to use the z-score for the lower. That's the 2.304. And for the upper, we're going to use that approximation of infinity. So 1 times 10 to the 99th power. All right, let's try it. So over here, I'm going to go see if I can get all this on the screen so you guys can see. There we go. We're going to go to second, vars, choose normal CDF. So that's 2. And now I'm going to type right over. So 2.304 is the lower bound. The upper bound, 1 times 10, raise it to the 99th power. So use your caret key, and then keep the 0 and 1. And then paste it. Hit enter, and the probability comes out as 0.0106 and so on. So they're saying, all right, what's the chances that she's going to swim more than 45 seconds? It's like a 1% chance. Because she's awesome. And it doesn't make sense that she would swim such a slow time unless she got like a cramp or something crazy like that. So 0.011 to the nearest thousandth would be the answer there. Right? So now that you've seen to use the upper bound as positive infinity, you could probably guess that here when it says use the same mean and standard deviation and so on, find the probability that the swimmer's time is less than 39 seconds, means that we'd be using the left end of the curve here. So if here's 39.7, swimming a 39 would be like right next to that. And then anything less than, I'd be shading below. So in this case, lower bound, upper bound, the lower bound, we're going to treat like negative infinity, which means we're really going to make it -1 times 10 to the 99th power. We're going to try to make that like a super, super small number. And then the upper bound would be the 39. So lower would go here, upper would go here. So let me write that over here so you can read it well. So normal CDF, the lower we're going to use is -1 times 10 to the 99th power. The upper, we're going to make the 39. Oops, I'm so sorry, not the 39. We got to calculate the z-score. Look at me getting all goofy over here. All right. This is where the handy dandy whiteout is helpful to have laying around here. There we go. All right. We got to calculate a quick z-score. Let's do it. So I can squeeze that up here. The z-score, 39 minus 39.7 divided by 2.3. That's going to be a tiny little difference. So when you take that difference here, 39 minus 39.7 and then divide it by divided by 2.3, we get -0.304. And here we go. Lower bound, upper bound is negative 0.304. The mean is 0. Standard deviation is 1. So we've normalized all of those numbers there. Go to your calculator. We go to second, VARS, normal CDF. Going to start getting good at this. This is now going to be negative 1 times 10 raised to the 99th power. This is now negative 0.304, 0, 1, hit enter again, and the probability comes out to be 0.381. So that's the chance that she would swim a time that's faster than 39 seconds or less than 39 seconds, which is pretty cool. All right, now the very last one, right, when it says the mean score on the ACT is 20.8, standard deviation of 4.8. Scores on the ACT follow a normal distribution. What percentile did a person who scored a 27 fall at? Same thing. All you would have to do is calculate the z-score. Okay? Why I do want to look at this one, though, is it doesn't say what's the probability. It says what's the percentile. So if you remember from the part earlier in the notes, percentile means you add up all the percentages to the left, all right, of that score. So let's draw this thing out. I want you guys to get in the habit each time you do this. What's up, Teddy? Of drawing out a picture to match it. Did you? Oh, you lose your ball, buddy. Here, hold on. What's your toes? Here it is. Here's your ball. Sorry. All right. Let's finish this. Okay, so the mean, 20.8. So dead center, 20.8. Standard deviation, 4.8. Scores on the ACT follow a normal distribution. Very important to know. A score of 27. Okay, so you're well above the mean. Nice job. All right. Percentile means we add up everything to the left. All right, cool. We have to create a z-score for this guy, which means observed score minus the mean divided by the standard deviation. All right, so when we do 27 minus 20.8 divided by 4.8. We get 1.29-ish. Should try to keep that one, whoops, kind of exact. So 2.9, maybe like 2. That's pretty good. All right, and now the lower, we're going negative infinity. The upper is now this guy. So when I'm looking for your work, because yes, I look at your work when you send me your homework. Don't send me a bunch of garbage. Right? I want to see things like the lower, -1 times 10 to the 99th. The upper, 1.292. The mean, standard deviation, right? The beautiful thing about creating the z-scores, those never have to change, right? Last practice, normal CDF, we got negative infinity up to 1.292. So almost 2 standard deviations above the mean. Hit enter, and look at that. 0.90 means that they are at the 90th percentile. They did better than 90% of all the kids that took the test. Nice job. All right. Thanks, guys. Try the homework out. Let me know if you have questions. Don't forget there is a Google Meet on Friday if you need it.